Okay, hang on. Hey, everybody, here's the warm-up. Sorry, I got distracted. Go ahead, get started. The warm-up is insert into a hash table. And here is our hash code. Hopefully, after our conversations, you're like, wow, what a not varied hash code. This is going to cause a lot of collisions. That's okay. We're keeping it simple because I'm asking you to do it as a human. But we're using strings as keys. The initial capacity is of size 5, but you must resize the array by doubling its size. We're not going to do the add prime thing. Again, we're doing it by hand. But you must resize before you hit a lambda of 1. And then draw out what the final array will look like. I am somewhat intentionally just using the terms so that we can all get more comfortable using those terms. But go ahead and take like the next 3 minutes or so, draw through the hash table. Any questions at the onset here? The Slido should be active, yeah? What's the lambda? Lambda I will define as the current amount of items in the hash table divided by the capacity of the hash table. Or you might see it on a slide as N over C. Any other clarifying questions? If not, we'll answer them afterwards. So go ahead, take 3 minutes, and we'll come back together. The Slido should be open. All right, if you haven't taken a guess at the Slido, now is the time. I guess I could pop over to the Slido, but maybe we'll just talk through it together. But I'm going to like open up the Slido thing now. Whoops. There we go. Hang on, we'll do this. Unhelpful. Okay, it looks like we have about 90 guesses, which might actually be how many people are in this room. Oh, 91, all right. Okay, I'm going to show our results here. Let's see. So in the hash table presented in the warm-up, in which bucket will the final entry of the string, quote, hello, space, world, end up? Aha, wow, okay, actually, I thought I was being so tricky, y'all. 1 is the correct answer for this context. If you didn't get it, don't worry, I was like trying to trick you in a bunch of different ways. So let's go back and let's look at the tricks. Okay, So here we go. Okay, so we've got strings as keys. We've got an initial hash table of size 5. So that string of just the letter A, in which bucket in this size 5 array is it going to go? Maybe fingers? Yeah, 1. 1 mod 5 is 1. Okay, what about the string AB? Which bucket is that going in? 2. Yes, I love it because 2 mod 5 is 2. Okay, now we've got the string of all C's there. Yes, 0 because there are 5 C's. So 5 mod 5 is 0. It fits perfectly, so it's going to go there. And then we've got the ABC string. Which bucket is that one going to go into? Yes, it is also going to go into the 1 bucket because 6 is the length of that string, and then we mod it by the table size, 6 mod 5, remainder of 1. Right now, we have a lambda of 4 over 5, so it's less than 1. But at the moment that I want to insert this 5th item, ABCD, if I were to insert that 5th item, I would then get to a lambda of 5 over 5. And we specifically said resize before that happens. So this is the moment when we're going to resize. So I'm going to double the size of the array. And then, remember, because I have a new size of array, and to know which bucket in the array it fits into, we have to base it on the table size. That means I need to go through and rehash everything from the size 5 table now into the size 10 table. So maybe we'll just go through the line again. So the string of A, which bucket in the size 10 table will it go into? Yes, 1. Oh yeah, I didn't do them different, but there you can see the 2 or the AB goes into bucket 2. 2 mod 10 is still 2. But now that we've got more space, we can see that that string of 5 C's, the ABC, those have now sort of redistributed. And this is looking better, right? We already eliminated 1 collision. That's the point of this thing. And now that we've got this, we're ready to add in the ABCD. Which bucket is ABCD going to go into in this size 10 array? Yes, 4. Yes, love it. There we go. Okay, then we've got the ABCD string. Which bucket is that going to go into in our size 10 table? Anyone? Yeah, I saw it. Great. It's going into 8. There's 8 letters in that string. And then, because I'm mean, I gave you the string of 5. Which bucket is 5 going to go into? 4, yes, because there's 4 letters in the word 5, even though it has a value of 7. So it will collide into the bucket of 4. And then finally, the answer that I put as the Slido, the hello world. So that hello world.length, what is that going to return me? What's the hash code that's going to come back from my hash code function here for this string? I heard it, yes, 11. So which bucket in this array does something with the hash code 11 get put into? Yes, 1. There we go. Hopefully this clarifies things a little bit. This is essentially what you are going to be implementing in P2, right? You've got to resize the hash table based on a value of lambda, somewhat of your choosing. You need to use linked lists as the separate chaining bucket structure. When you resize, you've got to do the rehash, all of that good stuff. Does anyone have any questions? Yeah.
Is there a difference in resizing before lambda equals 1, after lambda equals 1?
Is there a difference in resizing, like, right before I hit 1 or right before after? Like, for example, would there be a difference if I had taken that ABCD of 5 and put it into the size 5 array and then resized and redistributed? I mean, like, only in so much that then I would have to rerun the hash code immediately again on that thing. So, like, little unnecessary code. So that's why we're going to do it just before, and then once everything's kind of settled, then we move that stuff over. But realistically, not a huge, like, not some type of performance hit that will change the runtime. like complexity class at least. Yeah.
Could you go over why ABCD made lambda equal 1?
So this value of ABCD right here, previously, so we are calculating lambda as n over c. So when we put in A, our n was 1, then our n was 2, our n was 3, our n was 4. And so at that point, our n was 4, our capacity was 5 all the way along, as that was fine. And so it was like, you could kind of think in the code where this is maybe like there's a check in the put statement that's like, hey, if this is a new key and lambda is currently, and if like I update size, and then lambda becomes 1, before I insert it, double the array, move everything over. Any other questions on this? Those were really good. Okay, cool. I know this lecture is called Intro to Self-Balancing Trees, but I didn't finish the hashing stuff on Wednesday, so we're going to do a little more hashing, and then we're going to talk briefly about some trees. This was a bit in my plan because I knew this was kind of a light lecture day. Today we're going to talk about binary search trees. The reason we used to talk about binary search trees for a whole lecture is because binary search trees were not in 143, but they are in 123. So I'm going to kind of go over it for those of you that it's fresh to. And then next week, we are going to be learning all about some very unique and interesting tree formats that you didn't encounter in the intro series. Just our usual announcements. So remember that Project 2 is out now. It is that 2-week assignment. It's due Wednesday. Remember that it is a 2-week assignment, but I know what it's like to be a student, and so if I was a super on top of it student, I would be like, wow, I bet office hours will be a little lighter next week. If you have some questions, maybe you try to go next week, because the office hours the week following are probably going to get extra crazy for those of us that aspire but never quite seem to be as proactive as we wish to. The Project 1 turn-in, remember that we close 3 days after the initial due date, so I just heads up. The Project 1 turn-in does close on Saturday evening. And then Exercise 2, which is out, that will be due Monday evening, and we will release Exercise 3 on Monday. Any course administrative questions? I will also take this moment to tell you that the first assessment, I'm going to keep accidentally calling it a midterm because I'm used to having a midterm and a final, but remember that I changed it this quarter. You just have 2 exams. They're both worth the same equal weight, and they are not cumulative. So really, this is just exam 1. So exam 1 is going to be 2 weeks from today. That's right? It's week 3? Yes. So it is going to be 2 weeks from today. I will talk more about what the exam is going to entail probably next week officially. But 1, if you have a conflict with class, like, for example, I know info majors, a lot of you have capstone on Friday and things like that. Please send an email to CSE 373-instructors. We do have a couple options for makeup exam times, so we want to make sure that we get you the opportunity to take the exam. Also, please do remember that the exam will be an on-paper exam physically in this room. I know it's kind of cramped in here, but the room size is literally what dictates how many people can be in this class. That's just kind of how it works at UW, so we'll live. And then it will be an on-paper exam. You are welcome to have as many paper notes as you want, but nothing electronic. Did we, for fun, maybe put the midterm into ChatGPT? And did ChatGPT give it absolutely perfect answers? Yes, it did. Yes, it did. So we live in a weird reality. So it will be an on-paper exam. Remember that it is technically only really your first shot at the midterm, because what we're going to do is we're going to take your midterm, we're going to grade it, and then we're going to give it back to you on Gradescope, and then you will have a week to change any of your answers and resubmit it to earn up to half of the points you lost back. So let's say you had a really rough time on the first run of the midterm and you got 10% or something, you could still, earn back up to, somebody do some math for me, right? Love it. You could get a 55. That's a good score, right? For having a pretty bad experience on the first round. Or if you, I don't know, you crushing it, whatever. You got a 90% the first time through. Maybe don't even bother giving us the resubmission. But that's my sort of mitigation. Does anyone have any questions on sort of like the logistics of the exam at this time? I'm going to talk about the content more next week. Cool. Great. All right. So let's dive back into hashing. I just have a few slides to sort of follow up with here. So we have been talking about this special method called hashCode, where it takes in, or sorry, it usually doesn't take in a parameter. It's usually existing inside of every single object in Java. In fact, Java has this top level object, literally object with a capital O, that all other objects inherit from, and pretty much the only thing in that is the hashCode function. So Java has already added this method to the strings object, the character object, the arrays object, and it does all that fancy math of figuring out a unique int number to return back to you. So I know at the end of last lecture, we were talking about like what makes a good hashCode. Just so you know, you don't have to write your own hashcodes for the Java objects. They already exist. You could override them if you had something going on, but if you make your own object, you will have to write your own hashcode function, because this function's existence is what enables your object to be used in a hash table. So if you don't have this method, then you can't put your object into the like Java, HashMap object kind of thing. This is literally stuff I cut and paste from the official Oracle Java documentation. So I thought, it might be interesting. You could read through it. I'll let you read through it on your own time. But some of the basics of it is that the object class really just includes two things, an equals method and a hashcode method. If two objects equal each other, meaning if you have a situation where you have like object 1 dot equals object 2 and that returns true, then both of their hashcode functions need to return the same number. That's the rule of deterministic hashcodes. So it's just if we have like the same exact string, like if two strings are equal, their hashcodes need to be equal. Otherwise things will break and stuff will go weird. So for example, if you like override the equals method or something, you got to also override the hashcode function and vice versa. This maybe makes a little more sense if you imagine yourself writing your own objects. Like let's say you're writing some object that's like a student object and you've got the name and the ID and maybe their, like number of credits and the date of their graduation or something, and you have to decide like which of those pieces of information you evaluate when you're testing equality. Well, then you also need to take those pieces of information and transform them into some type of hashcode. I think that's everything I said I needed to say on this. Yeah, and like the reason you have to do these things is so that you could use the Java specific implementation of HashMap or HashSet on your objects. Oh, great. Any questions so far about that stuff? Let's maybe go to the Slido and see if there's the Slido. I keep wanting to like tab over, but I never actually function it that way. Let's see. Cool. Can't you just count how many inputs there are and compare it with the size of the hash table so you don't have to input them and then resize once it's lambda? This is a good question because, yeah, that scenario I gave you was kind of silly. Like you could see that I was asking you to put in 8 inputs. You're like, well, then why did we start with a hash table of 5? Sorry, imagine you are the writer of the hash table. As the author of the hash table code, you don't know how many inputs somebody's going to give to you, right? So you just kind of have to handle it as inputs come in. You're never sure how many more are going to come. So that was me getting you to practice that sort of experience of from the hash table function, you're just like waiting for whatever somebody gives you. You don't know how many inputs are necessarily coming down the pipeline. If you had a very specific scenario where you always knew, I'm going to hash things, but I'm always going to have this number of items, maybe you could write a really specific hash table. Will exam 1 have any code writing on it? That's a really good question. Right now, I don't think the plan is to have any like writing of code. I actually think it's kind of silly to like on paper without a compiler have to write code. I know we have to do it in some classes. We live in a weird system. But I will tell you, you may have to like look at code that we write and tell us what it does and maybe do some runtime analysis of it. You may have to remember the code behind certain items and the runtime of it so you can compare and contrast. But we're also going to have a lot of like sort of design evaluations. Like, oh, would you like to use this data structure or that data structure? That's kind of the general format of the questions. We have to write our own hash code in P2. No, I don't think you actually have to write your own hash code in P2. No. Right? Do you? No. I feel like I should know that off the top of my head, but my instinct is no. Thank you. Thank you, Simon. Thank you. Thank you. It's in the spec. Of course it is. How well does it work to just turn objects into strings in some way and just use that string's hash code? I'm not sure exactly what this question is about. Like if you're trying to say cast your object into a string. Oh, are you trying to like maybe, yeah, what, sorry? Oh, like object.toString and then run hash code on the toString representation of that object. You know, that's not a bad idea in some situations, but it depends on what that object's toString is. You know, like in an array, its toString is pretty representative of what that object is, but in the student example, maybe the student's toString only prints out the student's name and ID or something like that, and you need more information to generate the hash code. So that's not a terrible way to go about it. And also, you would then get the leverage of, I will say, Java's string hashcode function is very, like, it gives you a wide range and a lot of distribution, and it runs very efficiently. So leveraging existing implementations like that could be easier on you since they've already done all the fancy research and stuff. Yeah, question. Oh, like why do we have that thing where if we try to put in a duplicate key, it just like, oh, like it overrides the previous value for that key?
Yeah, I understand like that it does that, but why is that the case, and why do we not really care about the information?
So the reason that's the case, and this is an important piece about the differentiation between the ADT and the hash table. So we are doing that because we are specifically choosing to implement the dictionary or map, those are synonymous, ADTs, and for the dictionary or map to work, it has to have unique keys because it's all about lookup. So you can imagine, like, if you had duplicate keys, that's automatically a collision. And so by the definition of ADT, we're like, a dictionary cannot have duplicate keys. And so the way that we've decided to implement that within the ADT, like that sort of functionality, is just being decided that we'll always override the old key with the new, or the old value with the new one, mostly because it's more likely that over time you might update your dictionary. So, but you could imagine a dictionary implementation where it maybe sends you a warning before that happens or something like that, but that all comes from the ADT, not from the hash table. Great. Oh, this is an interesting question. When we're comparing two objects, instead of comparing data of two objects, can Java just compare the hash code? I love where this thought process is going, but I will say, even if Java's like hash code functions are still really good, just because two objects hash codes map or match does not necessarily mean they're equal. So it's actually kind of like not a bidirectional relationship. If they are equal, they better have the same hash code. But there could be a scenario where two different objects, like the math and the fancy algorithm and stuff, might produce the two same numbers even on different objects. Like in my bad, crappy hash code, the example would be if I use that length, like cat and hat would have the same hash code, but they're not the same object. That could still happen to Java's hash code. It's just a lot less likely. So that's why we still need to use the equals method for actual comparison. An object, yes, is an abstract class. For that person asking. Yes, you can't actually instantiate an object. It is literally just there to force the structure of things. Great questions. These are really good, y'all. Okay, let's continue on. So we have now talked a lot, and like I sort of consider that the end of the hash information that you need for Project 2. But there's actually a bunch of other interpretations and designs behind hash tables. So I just want to spend a little bit of time so you have a full picture of what a hash table is. And like I said, part of my sort of reasoning behind this is because I hate to say it, but like, gosh darn it, if hash tables just aren't the most popular data structure, Like, they are probably the data structure you are going to use the most, encounter the most. It'll be in interviews the most. It's just that constant time lookup is so good. It's not always the perfect fit because we lose like ordering and stuff, but it comes up a lot in software in general. So I just want to give you a full picture of what hashing means in computer science. So, great, thanks, weird animations. I sort of mentioned that there's a lot of different design choices. We had made the design choice that when a collision happens, we'll just like turn each of the hash table buckets into a collection so you can store multiple things there. But there's another way to handle collisions called open addressing, where instead of just holding multiple things in one bucket, if a bucket is full, we just go find a different and open bucket to put it in. But the way we pick the next bucket to put it in, there's even more ways to design that. So the first one, so this is open addressing. The first way to find the next possible bucket is something we call linear probing, which is if you look at this code, we get the hash code for something. We mod the hash code by the array length. Hopefully that's something we're comfortable with. And then we look and we see, hey, if that index that I'm looking at, if there's something already in there, literally just like look next door. So if I have a hash table and these are a set of keys, I put 1 into my hash table. I put 5 into my hash table. I'm ready to put 11 into my hash table, but the bucket it wants to go to is the bucket 1, and it was full. So I just need to find the next closest neighbor that's empty, which happens to be my next door neighbor too. So I put 11 there. Great. I'm going to hash 7. I want to hash 12, but that bucket is full. So I just go to my next door neighbor. Then I want to hash 17. Oh no, another collision. Next door neighbor. I want to hash 6. That's fine. It goes in there. But then if I want to hash 25, I want to put it in index 5 full. So I look next door. 6, full. 7, full. 8, full. It goes into 9. Any questions? Yeah. So if that's how we put things in, we just reverse to find it. So we do the same kind of code where we find where the natural hash is, and if it's a full box, but it's not the key I'm looking for, then I will just start looking at all of the neighbors until I either find it or I hit an empty box. So if I look where it's supposed to be and then I loop through all my neighbors until I hit an empty box and I never find it, then I know it's not in the hash table. Okay, great. Apparently I had more examples. Oh, I know I have this example. Okay, let's talk about another sort of situation with it, which can be interesting. So if I try to hash 38, it goes in there. I try to hash 19, it goes in there. Great. I try to hash 8. Uh-oh, it's full. So I loop around and I linear probe all the way back to 0. And then I try to put 109 in there, but it's full. So I loop around and then I try to put 10 in there. And so what I end up with here is the problem is we can end up with what we refer to as clusters. So if we kind of get a lot of collisions in the same general area, since we're just putting it like right next door, I can end up with this kind of situation where I have sort of like clusters of full boxes and then big gaps. Causes one long chains of occupied slots within a hash table. So when we think about the runtime for linear probing, when is the runtime really good? No collisions. That's always the best. The best case scenario in any hash table ever is 0 collisions, because then it's just constant time. Great. But when it's bad is when we hit a cluster. You can also think of this as like, imagine you hit in the separate chaining example, a really long linked list. That's kind of like when the worst run case is going to happen. The cluster is sort of like a long linked list, sort of parallel here. Maximum load factor, like what is the maximum load factor that's even possible? Remember with the separate chaining, there was no enforcement of load factor. So we kind of had to make a design choice as to when to resize. This is not the case here. Like we only have this many spots. So we have a literal maximum load factor of lambda of 1. So insert a bunch of smart people all over the world have done the research on this. We actually do need to end up resizing more often in the linear probing scenario, so we typically resize around a lambda of 1/2 for the linear probing situation. Otherwise, we might get a pretty poor runtime with all those clusters. Gosh darn it. Isn't that annoying, those silly clusters? Is there another way? Yeah, here's another open addressing solution, and it's called quadratic probing. And as you can see down here, what it is instead of just looking to my immediate neighbor, I add in this sort of quadratic look so that instead of just putting clusters of neighbors, I kind of like try to find places that are a little more spread out. Okay, let's look at an example. So I put 89 into the table. I put 18 into the table. I want to put 49 into the table. It wants to go into index 9, but it's full. The first round of quadratic probing is still just kind of going to look next door because 1 times 1 is 1. But if I try to put 58 in, well, it wants to go into index 8, but that's full. And then it wants to go into index 9, but that's full. And so then it wants to go into index 2. And look, we've kind of like left a gap now. So we're kind of like avoiding that little bit of the cluster there. We're less likely to, we're sort of distributing the cluster along. And then here you can see 79, 27. I'll let you sort of do that math. But this is just a way, it's literally just trying to mitigate those sort of like clusters by picking a way to sort of distribute where I look for the next empty bucket. But because I, in this scenario, might not always look at every single available bucket, because I'm kind of like looking at a certain set of buckets, the way the math works for this is that you can accidentally hit an infinite loop. Because I'm going to constantly be sort of like doing this quadratic thing and then modding by the table size, I might only be looking at like 4 possible boxes within the array and just constantly adding numbers, and because of mod by table size, I'm just looking at those 4 over and over and over again. So this actually is something we can avoid as long as we ensure that we resize at a lambda of like 1/2. So you will find that a lot of people they actually choose to resize in quadratic probing at a lambda of 1/4. That's a common sort of style for that. You still can get clusters. I think I have a thing. Did I put it? Secondary clustering is the name of what happens when you get these sort of clusters around the items. I think this is just another example of how you might get into that infinite loop. But I will say quadratic probing is not super popular, but now you kind of get an idea behind the design of how we're trying to mitigate things. And every time you solve one problem, you probably introduce another. And that isn't necessarily a bad thing, but it means whenever you are designing code, you are constantly thinking about these trade-offs. And you have to be very aware of what works best for your situation. So I'm just trying to fill up your toolbox. If you're like, Casey, what's the best hashing collision resolution strategy? I don't think there's a one singular right answer, but there might be a right answer for your data set. So this is how you have a good toolbox, and then you win those arguments in the dev rooms when you're arguing about which way to go. Cool, we talked about that stuff. Any questions so far on the probing pieces? Yeah, in the back.
Is there any way we can make the collision solution, like we can do quadratic probing with linked lists together?
With linked lists together? Yeah. In that situation, what would you do?
So let's say I do a linked list,
Uh-huh.
and I want to do a quadratic probing as well. When quadratic probing like collide and enter an infinite loop, just put it to it.
Oh, like we do a sort of check to see, have we already checked this box before? If I've already checked this box, I'm in an infinite loop, so maybe let's just make this box a separate chaining. You know, no one has ever proposed that to me, but I could totally see how that would technically work. I would be curious as to see how the like runtime works on it. You know, it's all these things where like, because of the trade-offs, there's no like objectively like, oh yeah, that would like resolve the runtime of it, but maybe for that scenario it could. I would guess in that situation, you would very, very rarely have a chain longer than 2, which would be nice. So, but yeah, you could kind of do some weird mix and match. In fact, here's my final hashing, and then I will tell you how Java implements their hash table and they do a little bit of a weird mix. So the final hashing collision resolution strategy is what we call double hashing, which is literally just if the bucket you were trying to hash to is full, here is a whole separate hashCode function that you run on it instead. And so the way that people usually do that is maybe you have like a really efficient hashCode function that may produce a few more collisions, but you want to keep it super efficient because that initial hashCode function you're going to run so often. But then in the event of a collision, maybe you have a second hashCode function that takes a little bit more time, but has a lot more of a varied set of numbers. And you know, like you could spend a little bit more time calculating the hashCode in that one because it's only going to be run in the case of collisions, which is hopefully a lot less frequent. So double hashing is also a very popular hashCode collision resolution strategy. Cool, great. Like I've mostly talked about this. Like I said, I sort of leave these slides so that it can be just sort of standalone. You could read them. Yes. Great. This is another one, a standalone slide. Great, great, great. But here is what I was sort of talking about. This is how Java has chosen to implement their HashMap. So one, they start with a default capacity array of 16. The reason they do that is literally this paragraph I cut and paste from the Java docs. They did a bunch of research about the proportionality, that trade-off between how much empty space, how many boxes you might have to iterate over, and how often you have to duplicate it. And 16 is their magic number. So I know I kept using 10 as my initial default underlying array to make your math easier because it's easier to mod by 10. But they use 16 because of these reasons. They also do resize at a load factor of 0.75, again, for these exact reasons, which is mostly like 0.75, and their research tends to be this nice tipping point between empty space, the number of buckets you have to loop over, and redistributing to avoid collisions. And then the way that it handles collisions is it initially does use linked lists as the buckets. So you can see that like what I'm asking you to write is almost identical to Java's implementation, but after 8 collisions, and the number 8, I tried really hard to find why they picked 8 to be the magic number of collisions. I could not find an answer anywhere on the internet except that it was introduced in Java version 8. That's my suspicion. But after specifically 8 collisions, then the table will resize and it will transform all of its buckets from linked lists to something called an AVL tree, which is what we're going to learn about on Monday. So instead of using linked lists, it uses a whole different structure for the collisions that it's going to hold. So it always uses a sort of separate chaining, but it first starts with a set of linked lists. If you get too many collisions, then it transforms to a more efficient data structure. Any questions about this? Yeah? Yes, thank you. Load factor is lambda. So it resizes at a lambda of 3/4. Good clarifying question. I'm pretty sure they mean 8 collisions total across the hash table. That's when it transforms into an AVL. Yes. Because 8 collisions in one bucket, that's a lot. Then you got something real funky going on. Cool. Yeah? They do. They keep a count of how many collisions are happening. Yes. Cool. Okay. This is just a slide. The term hashing, remember, it does not necessarily mean this table where we do the buckets and stuff. Just like the term hash means to take a object, an item, and transform it into a specific range of int values, which is super convenient for computers everywhere. So here's a bunch of other situations in which hashing shows up outside of hash tables, or that we use hash tables in. I think there's a bunch of fun stuff in here. You can read it, but I think the ones that are probably, at least in my point of view, pretty interesting. One, cryptography. So for example, if you type your password somewhere into like your web browser computer, what it will do is whenever you're transferring information across like the tubes of the internet, it's kind of dangerous. Somebody could like listen in on that tube, or it could get lost or something. So it's very common for somebody to hash your password on the front end and then send it down along the line for the to the internet, and then when it gets to your database, then you unhash it and you store it in the database. Or sometimes they'll store it in the hashed version in the database, and they only unhash it when somebody requests the password to get checked. Or, remember, you could kind of compare hash codes, but it's not deterministic. So cryptography is just another way. Hashing is a way to sort of obfuscate whatever that string or that item you're trying to use is, because it's just a way to take that object, transform it into an int. It doesn't look so much like that object anymore. Another way that we use hashing is actually compression, too. So again, it's like a way to sort of translate code on one side that can then be retranslated on the other. So if we're going to say, compress a bunch of video files, what they will do is they will go through and they will make a bunch of hash codes representing all of the information, and instead of sending like that hefty video, they'll send this like long string of numbers, and then when you extract it, what it's really doing is just reversing the hash. And that's, again, kind of like what our hash table was doing, right? Like, when you give me a key, I hash it into the table. When you ask me to get the key out, I kind of reverse engineer the hash. That's what's happening with the compression as well. I'll let you read this. I think it's fun. But this is sort of the end of our hashing content, and I have taken until 4:13. Does anyone have any questions? Okay. I am going to talk about binary search trees for 7 minutes, but you are also very smart. I promise you, you can learn what you need to learn about binary search trees in 7 minutes. So remember, this is a tree. Tree, by definition, is literally just a node that points to some other branches of nodes that then point to some other amount of nodes. It is typically inherently recursive, and that each node, it is itself sort of a subtree of other trees, so on and so forth. You will see we almost always use what we say are binary trees. Binary trees are nodes that point to two or bi children, like a left child and a right child. But you can have trinary trees, and you can have n-ary trees. But I'm not going to subject you all to that until maybe the last week of class, so we are going to only talk about binary trees in this particular context. So this is mostly review from intro. You've got a data piece, you've got a left, you've got a right. Trees, the way that we think about runtime very often is dependent on this concept of height. So this is just a slide that talks about like, oh, for some math reasons, if your overall root points to null, that is a height of -1. If it is just a singular node, I think of it as like a bulb. It's not really grown. It's got no height. And so really, I count the height by the number of levels after the original node. That's not interesting. So finally, binary search trees. So a binary tree is a collection of nodes that all have either 0, 1, or 2 children. That's sort of the definition of a binary tree. A binary search tree adds what we call an invariant, which is just sort of like a rule. And the rule states we are going to store information in the binary search tree in an ordered manner. And the order states for every individual node, every node to my left must be less than, and every node to my right must be greater than. So it also applies recursively. You can see in our example here, 9 is the overall root. 1, 3, and 5 are less than 9. But if we look at 3, 1 is less than 3, and 5 is greater than 3. But the collection of 1, 3, and 5 are all less than 9. And the collection of 10 and 30 are all greater than 9. But 30 is greater than 10. So on and so forth. So it's a recursive sort of definition. But what's really nice about it is that it gives us a deterministic way to move through the tree. This is an aside because if you can't tell, I'm just using numbers here, but I am going to be talking a lot about how to implement the map ADT, just like we've been doing with our hash tables. With hash tables, I would give you little parentheses and then like a thing, comma, a thing. You can imagine a binary search tree node that's like this, where it's got, you know, 2 data fields, one that's the key, one that's the value, and then it's got 2 child node fields, a left and a right. But because I cannot fit it on slides, you're going to see I just sort of like only talk about the keys. Hopefully after the hash table examples, you're like, we just care about what's happening with the keys. The values are along for the ride. So that's why you're going to see my nodes will disappear one of these fields. I'm just not showing you the value, but I'm still talking about a map. So let's say we are performing containsKey on a binary tree that's on the left and a binary search tree that's on the right. So here's my keys. If I'm trying to find 5, without a binary search tree, I'm like, is this 5? Nah. Is this 5? Nah. And then I check everything. Is this 5? Nah, 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 nah. I have to check every single node in the tree because there's no specific space where the 5 is going to be. It's like a linear search, but it's not linear because it's a binary tree, but it's like a whole tree search because there's no specific place to find the 5. The magic of the binary search tree is very similar to the magic of binary search. Oh, remember with binary search how we like started in the middle and then we're like, are you less than or greater than, and we eliminated half the things? That's exactly what's happening with this tree. So if I'm looking for the value 5, I come in and I'm like 9. Oh, the thing I'm looking for is less than you, so I am going to go to the left. And I'm like, oh, 3. The thing I'm looking for is greater than you. Boom, I found 5. So when I think about the runtime to find something, it is dramatically different. I like to think of each of the nodes as like little signposts. And each time I go left or right, I eliminate whatever's on the other branch as the direction I have to look. This gives me like a very specific way to move through the tree to find the thing I'm looking for. Questions? That's it. That's what a binary search tree is. Okay, great. So on Monday, I'm going to tell you how we can make this binary search tree even more performant. We're going to meet the AVL tree. Have a great weekend, everybody. I will see you on Monday.